When 15 supernovae explode in close proximity to one another in both time and space, it makes a huge bang. It should come as no surprise that such a violent incident would drastically alter the area of space in which it happened. The interstellar dust was carried away by the power of those simultaneous explosions, producing a massive void of low-density matter and a shockwave that is still traveling at a speed of 6 kilometers per hour across the galaxy. Secondly, plasma reached a temperature of 1 million degrees Celsius in its wake. It's the simultaneous heating of the interstellar medium and Swiss cheesing that is currently referred to as a hot bubble. It symbolizes both the demise of stars and their beginning. However, this isn't some far-off building that lurks in the distance. It's a region of the cosmos. It's not even directly in the path of our solar system. We're in it, charging headfirst toward its point of origin. Greetings from our local hot bubble. Scientists now understand that the local surroundings of our solar system. We live in a neighborhood. It's still being investigated, but its nature is becoming increasingly apparent. What then? Are we aware of the local hot bubble? How did it come to be? And what else is there to be found? You're watching Astrum, and my name is Alex McCohen. Join me as we stroll through the aftermath of star explosions and discuss how scientists even came to the conclusion that we were initially in the midst of a cataclysm. We weren't always aware of the local hot bubble. Initially discovered in the 1970s when low-energy X-ray emissions were found throughout the sky, the local hot bubble was believed to be a superbubble, a sizable void in the interstellar medium filled with low-density, tenuous gas at 1 million degrees. During the 1990s, researchers discovered that wherever neutral atoms interacted with the solar wind, X-ray emissions could occur, challenging the notion that a sizable hot bubble must be indicated by the emissions. However, soon evidence would demonstrate that the decades-old theory was accurate. Emission from the DXL local galaxy mission. Although comets and other sources can produce soft background radiation, for example, the mission found that only 40% of the fog of low-energy X-rays came from within our solar system. This confirmed that the dominant source was diffuse X-ray emissions from the LHB, a 1 million degree interstellar plasma region. The LHB. Even though this confirmed the bubble, there were still unanswered questions about what could produce such a huge void and what might explain the thousands of surrounding young stars. The prevailing answer proved to be both violent and intriguing. Recent research indicates that the local hot bubble was caused by roughly 15 supernova explosions in a row over several million years, erupting near one another. According to scientific estimates, the first of these enormous stellar explosions occurred about 14 million years ago. They released massive amounts of energy, driving out interstellar material and raising the temperature of the residual gas to extremely high levels. Evidence of the geological record of our planet contains remnants of these ancient explosions in deep-sea sediment deposits in the shape of iron-60, a unique isotope. This radioactive isotope can come from a variety of sources, but the most typical source of iron-60 is thought to be explosions from supernovae. We know that the isotope's source is from outer space because iron-60 can't be made on Earth by itself, and similar deposits have also been found on the Moon. What makes this radioactive isotope unique is that we know how long its half-life is. We are aware that it decays into another radioactive substance called cobalt-60 isotope, prior to its eventual decay into the stable element nickel-60. The half-lives of iron-60 and cobalt-60 are 2.6 million years and relatively short, respectively, only 5.3 years of half-life. As a result, when we discover a deposit that contains these components, scientists can compare the concentrations of cobalt and iron-60, 60, and nickel-60, which function as an elemental clock to show when that substance was deposited on Earth. Fortunately for us, international research groups have discovered a number of these deposits during the previous few decades. Iron-60 deposits were discovered in deep-sea crust samples collected in 2016 from the Atlantic, Pacific, and Indian Oceans. showing two separate peaks in the radioactive debris that indicated a number of recent supernova events. Additionally, not too far from only 326 light-years from our solar system, the sample revealed an iron 60 spike that occurred between 3.2 and 1.7 million years ago, as well as another 6.5 to 8.7 million years ago. Anton Wallner, a nuclear physicist who led one of these research groups examining the deposits, said that the more recent debris was dispersed over 1.5 million years, indicating that a sequence of supernovae occurred one after the other, in quick succession. Dieter Breitwert, an astrophysicist who led a second group of researchers, determined the most likely cause of these supernova explosions, which would have happened 196,123 light-years away from the Sun. These supernovae that produce the local heat, it's possible that the bubble belonged to an aging star cluster whose surviving members are currently connected to the stellar group Scorpius Centauri. Using the iron 60 deposits, the researchers were able to track the signals of two supernovae, one that occurred 1.5 million years ago, and the other 2.3 million years ago, due to the demise of stars with masses 8.8 and 9.2 times that of our own Sun, in that order. Actually, our LHB is still expanding today, even though it happened far more slowly than it did millions of years ago when the supernova exploded. The growth rate has reached a plateau at roughly 6 kilometers. Astrophysicist Catherine Zucker now claims that in 2022, Zucker wrote a groundbreaking study that recreated the development of our galactic neighborhood, following the chain of events that gave rise to our local hot bubble and all of the young stars that are visible in the area today, after they discovered something amazing there. Using information from the European Space Agency's Zucker and her group, created a three-dimensional space-time map using the Gaia telescope. They demonstrated that all of the young stars within 500 light-years of Earth and the surface of our local hot bubble contain star-forming regions. Using these three-dimensional locations and the three-dimensional movements of the stellar clusters, we traced back to near our local hot bubble, where there is a 20 million year history of star formation. It was evident from the implications that all of the well-known star-forming regions near our solar system had developed along the outer edge of the local bubble as it expanded and collected gas. We are constantly learning more about the field of stellar nurseries, especially when fresh photos are captured by our observatories. This is an amazing picture of the Chameleon 1 dark cloud, one captured by a dark energy camera on the Victor M. Scientists can extract information about how stars form from the propagation of starlight from within it, which could help us comprehend the current effects of local hot bubbles on our galaxy. Perhaps you haven't seen this specific image before, as new space news is coming out all the time. But I recently started a newsletter to help you stay up to date on all the amazing pictures that our numerous telescopes in orbit and on Earth capture, or innovations that transform how we comprehend the universe. Even if the headlines do, you should sign up to ensure that you never miss the most exciting news by following the URL in the following description. Every Thursday, new editions are released. Zucker and her associates discovered 4 epochs of local hot bubbles that originated 14 million years ago. Formation of stars on the bubble shell. Starting roughly 16 million years ago, we observed the formation of the UCL star cluster, or Upper Centaurus Lupus, after these formed about 49 light-years apart from one another. And about 14 million years ago, these stellar populations were the source of the stars that went supernova to create our local bubble. About 10 million years ago, we see the first of the 4 star-forming epochs following the establishment of the LHB. The association between Upper Scorpius and older, these formed at a distance of roughly 49 light-years. Additionally, roughly 10 million years ago is when the first of the 4 star-forming epochs started. Then, some 2 million years ago, the stars in Chameleon and Lupus, as well as these stellar populations, produced the stars that went supernova years ago to create our local bubble. Current time is within the 4th stage of star formation. Period. The dense, star-forming molecular gas that surrounds the LHB, which will ultimately result in the formation of additional star clusters along the outer edge of the bubble. With all of this magnificent creation, you may be shocked to discover that we are intruders. Our sun did not form within the local bubble. The sun was actually 978 light-years away when the first supernova only joined the LHP approximately 5 million years after going off in the UCL and LCC. It entered the bubble years ago as it traveled through the galaxy. Using the it entered the bubble years ago as it traveled through the galaxy. Using the you can see our sun's location right before it entered the bubble by looking at its trajectory, which is represented by yellow dots. And now, simply by coincidence, our sun is situated close to the LHB's center. As scientists drifted into the center of what had once been a blazing furnace, they became interested in charting the local bubble's continuous temperature. You may be wondering why we're so at ease if here, plasma temperatures can rise to 1 million degrees Celsius. The density of that plasma is crucial. Check out this 3D map of our local hot bubble from Zucker's 2022 publication. In a deep blue, our bubble's density is incredibly low, comprising roughly 100 times less hydrogen than the average interstellar medium. Thus, diffuse X-rays are produced when the temperature of this gas rises to about 1 million degrees Kelvin. We don't need to be concerned about the emissions we have seen throughout the entire sky. Additional proof of the local bubble's existence has come from monitoring its temperature. The RINEN extended survey using the E-resistor X-ray telescope and imaging telescope array has collected the most comprehensive soft X-ray survey of the entire sky to date. Additionally, that information has been utilized to map our solar neighborhood and the LHB in far greater detail than previously. Launched on board the German-Russian joint mission Spectrum RINEN Gamma, or 2019, saw Spectre RG. Rosita X-ray telescope data has enabled a group of researchers led by the Max Planck Institute for Extraterrestrial Physics to produce a 3-dimensional map of the LHB. This temperature dichotomy could be explained by supernova explosions in the past few million years. Additionally, by producing this bubble map, the team also discovered that the LHB extends towards the poles of the galactic hemisphere. This is because the hot gas in the bubble expands outward in the direction that encounters the least amount of resistance. Stay away from the galactic disk of the Milky Way. In addition to determining the temperature variations and the bubble's shape, the group gathered this information along with additional data to make a map of our galactic neighborhood that is even more detailed. In the latest 3D, our local hot bubble appears on the map as a 3-dimensional splatter encircled by and even intersecting with other galactic formations. These additional structures symbolize known supernova remnants, such as the red-colored Gum Nebula. Here, dense molecular clouds are displayed in orange. In our galaxy, they form a Milky Way that resembles Swiss cheese. What a massive supernova blasts out the cavities in our Swiss cheese galaxy. Explosions where the holes left by dying stars are filled with new stars. Additionally, it resembles Swiss cheese. Our local hot bubble might be a component of a complex web of related characteristics throughout our galaxy. The Canis Majoris tunnel, for instance, spans our entire galaxy. The Canis Majoris tunnel, for instance, is thought to link our local hot bubble to the Gum Nebula or another object on the Milky Way's galactic disk. Greater superb bubble in the vicinity. However, the 3D map also showed another earlier unidentified interstellar passageway leading to the constellation Centaurus, potentially linking the nearby Loop 1 superbubble to our local bubble. While these interstellar tunnels are tantalizing, our current understanding of them is limited. Nevertheless, these tunnels of hot gas and bubbles of star formation, shaped by the death of gigantic older stars, have me in awe of I'm in awe of the tunnels of hot gas and bubbles of star formation formed by the demise of massive older stars. The evolution of our local galactic neighborhood is truly powerful and interconnected. He proposes that the environment is continuously shaped by the energetic output of stars, which are not merely born and die in isolation, for millions of years following their death. Additionally, as our instruments for observation become more sophisticated, we are beginning to uncover the extent of these hidden structures. So next time you look up at the night sky, you might remind yourself that we are encircled by bizarre patterns. Similar to the Milky Way's local bubble, remind yourself that we are surrounded by ancient cataclysms. Additionally, some of the stars you see are actually plastered along the walls of a cavity that was blasted by a supernova and connects to other areas of the galaxy via interstellar tunnels. Whoa. Imagine for a moment that you're looking out your window when a singular bright light, could a nearby supernova destroy Earth, suddenly flares into existence in the sky above you. This dazzling star is visible during the day and is as bright as the full moon at night, if not brighter. You may already be in danger if you can see the light, because that unexpected star is currently bombarding Earth's atmosphere with a devastating amount of X-rays and gamma radiation, destroying our ozone layer and exposing us to the full force of the sun's lethal radiation, and abandoned at 10,000 while traveling, to 40,000 km corpuscus, a cataclysmic wave of stellar matter and debris barriers in the direction of our planet. An exploding star's dying roar, billions of tons of flaming mass at us, prepared to sweep across the surface of our planet. Emerge as a tidal wave of flames. It's a supernova, or it's at least one interpretation of what we might witness if one were to happen nearby. However, how likely is it for this to actually happen? What constitutes near us on a cosmic level? How close would a supernova explosion need to be to endanger life as we know it? What could we on Earth actually experience? And what stars near us have the potential to detonate in this way? I'm Alex McCohen, and you're watching Astram. Join me today as I discuss an event that could be an Armageddon in our lifetimes, or could be nothing more than a pretty twinkle in the sky. Let's begin with the positive news. Supernovae in our galaxy are not that common. While astronomers observe hundreds of supernovae every year outside our galaxy, this is mostly a reflection of how many galaxies there are in the universe. Closer to home though, within our own Milky Way, we likely only see every century there are approximately 2 to 3. This means that the chances of one going off tomorrow are not particularly high, but they are not impossible. Archaeologists believe that the Earth has been hit by a supernova in the past, throughout its 4.5 billion year existence. For starters, we exist in the local bubble is an area of space that is sparsely populated, of interstellar space about 1,000 light years across, which is thought to have been carved out by a supernova. Detonation 10 to 20 million years ago, during which time our planet would have existed. I discuss it in another of my You Can Watch the Videos here. Scientists have discovered evidence of another detonation that occurred 2.5 million years ago due to a high concentration of iron-60 and manganese-53 in a specific layer of the geological record. This supernova occurred far enough away to be harmless to us, but this may not always be the case. Some scientists believe the extinction of woolly mammoths was caused by a massive piece of debris from a supernova that crashed into the planet approximately 13,000 years ago. The impact site in question contained magnetic sphericals and radioactive potassium-40, a substance found in the supernova ejecta, a smoking gun in the age when most mammoths became extinct. Even before that, mammoth tusks from 34,000 years ago were discovered containing tiny impact craters formed by grains of slightly radioactive iron traveling at 10,000 km/s. If you recall, this was one of the potential speeds at which supernova explosions could travel. That couldn't have been pleasant experience for the mammoths in question. However, a keen observer of this situation may notice an important fact. Clearly, if life began on Earth approximately 3.7 billion years ago, and we faced my condolences, woolly mammoths, if you did die out from one of these, then supernovas as a whole can't be quite as destructive as my initial introduction made them appear to be. And this is largely true. Despite this, of course, it comes down to proximity. If I'm 1,000 kilometers away from a nuclear explosion, there is little to fear. But it's a different story if one goes off on my coffee table. When it comes to supernovas, it turns out that the universe has fairly large coffee tables. To understand the scale of these explosions, we need to understand the forces involved, to better understand how supernovae occur. It turns out that there are two main paths that stars can take to reach that explosive grand finale. Although in each case, it has to be the right kind of star. For the first path, a white dwarf is typically required in order to produce a Type 1a supernova, a binary system that is siphoning matter away from its neighboring star, either slowly or quickly, until it reaches a critical mass point. Although the exact nature of this path is unknown, it is believed that a white dwarf, or a massive star, that is primarily made of carbon. Typically, the diamond core is ultimately balanced between two strong opposing forces: gravity, pressure, and electron degeneracy. This simply indicates that atoms typically object to excessive compression. Electrons prefer to remain at specific distances from the atom's nucleus, and will not be forced to become denser than this idea. However, gravity is a very strong force that tries to attract matter closer, especially in a white dwarf or other dense mass, where a portion of the mass of a sugar cube is equivalent to that of a car. Additionally, in a binary system where the white dwarf eventually succumbs to gravity as it absorbs more and more matter from its nearby star, the entire house of cards collapses at once due to electron degeneracy pressure. Carbon fusion begins. In a few seconds, the majority of the star undergoes fusion, transforming into heavier elements and releasing a massive amount of energy as, what is the energy level? Approximately 1/4 of a rotarillion joules. That's the one followed by 45 zeros. If you say you were familiar with that number, you're most likely a liar. In a matter of seconds, all of this energy is released. Consequently, the star ejects all of its contents in all directions, causing it to travel at a speed of 6%. This event burns for a few weeks and is 5 billion times brighter than the Sun, until the total energy level has begun to decrease due to the ejector's distance traveled. Type 2 supernovae are comparable, but they do not involve a white dwarf, which is a star that is at least 5 times more massive than the Sun at the end of its life. These stars continue to shine brightly. Furthermore, the star's equilibrium is maintained by the heat of fusion as well as electron degeneracy pressure. But balance eventually collapses, much like a Type 1a supernova. The star runs out of fuel this time, and in the absence of this extra fusion energy driving the star's mass outwards, electron degeneracy pressure on its own cannot cope with the star's weight to a similar effect. The only outward, the weight of the star cannot be handled by electron degeneracy pressure alone. The difference is that although some of a massive star will survive, it often collapses into a neutron star or a white dwarf, while black holes and white dwarfs typically disappear entirely. In any case, a supernova releases enormous amounts of material and energy. It is so large that, naturally, anything right next to it won't endure a long time. This energy is powerful enough to destroy a star. A world won't stand a chance if it's close by. Fortunately, our Sun will never explode as it is not massive enough. But if it did, there is a good chance the Earth would be either partially or completely evaporated. Temperatures of 15 degrees cause its rocky exterior to boil, times hotter than the Sun's surface and being carried away during the supernova's final weeks. The speed at which this initial wave of destruction would fade with distance, however, is unexpected. Yes, in reality, vaporization is not the greatest danger posed by supernovae. 2011 saw, according to calculations made by University of Cambridge experts, even planets orbiting their star at a distance of 15 billion kilometres, or roughly 100 times the distance between the Sun and the Earth, would not change, and would just, now that there wasn't much left to orbit, they were launched into space. Naturally, the hypothetical ecosystem of such a planet would likely face different issues. Things would become extremely cold very quickly. Naturally, even if a planet's crust itself remained unchanged, it does not imply that life would be sustainable on that planet. Disregarding the light of a supernova, sometimes exceeding the brightness of an entire galaxy, rendering anyone who witnessed it blind. Eliminating our atmosphere alone would cause problems. High radiation levels, even if they had no direct effect on us, would alter the chemical composition of our atmosphere, destroying the ozone layer and significantly increasing our likelihood of dying from radiation poisoning, eliminating phytoplankton in the ocean, and causing mass extinctions as the effects trickled up the food chain. Scientists estimate this kill zone to be within 25 light years. Above that, as a supernova gets farther away, its fury starts to subside, itself away. However, the asteroid that might have killed the mammoth originated from a supernova that was 250 light years away. If it happened at all, it was likely just bad luck. Generally speaking, we wouldn't notice any damage from a supernova this far away. Its radiation levels would not be high enough to trigger widespread extinctions. We wouldn't even be aware of the event at 500 light years, other than perhaps seeing a brighter star in the sky. Which leaves one crucial question. Are there any supernovae within 300 light years? Candidates that we should be concerned about? Fortunately, scientists are reasonably certain that the answer is no. Huge Betelgeuse and Antares are the only stars that have the potential to explode as supernovae. More than 400 light years separate those two. White dwarfs are a little more difficult because of their reduced speaking. There wouldn't be any damage from a supernova this far away. There wouldn't be enough radiation from it. But in 2013, the Gaia Space Observatory of ISA published a huge packet of data in its attempts to map the stars, which enabled researchers to locate 13,000 white dwarf stars in we are 326 light years away. Fortunately, despite this high number, scientists keep in mind that none of these are expected to blow up anytime soon. Soon refers to the next few 100,000 years. In relation to Betelgeuse, there are a few. According to scientists, this red giant could explode much sooner than that, possibly in the next few years. The premise of their research is that Betelgeuse has a significantly greater radius than anticipated. However, if it's accurate, it could indicate that we would have the opportunity to witness a nearby supernova during our lifetime. Of course, some models state that we would be worry-free. It would take some time for the shockwave to leave Betelgeuse. To us, and even when it got there, the solar wind's push would be more powerful than its own. In other words, neither our atmosphere nor our magnetosphere would have protected us. The shield of the suns, such as supernova, could be prevented by the heliosphere alone. So there you have it. While supernovae are perhaps some of the largest explosions in the universe, through some fortunate stroke of luck, our patch of galaxy has nothing really to fear from them. The odds of us being hit by even the neighboring stars like Betelgeuse that are scheduled to go supernova are incredibly small. The nearby stars that are expected to explode as supernova, such as Betelgeuse, are extremely tiny. Indeed, Earth has a lot of natural disasters like hurricanes, earthquakes, and floods that can destroy a community in a heartbeat, and space remains a hazardous environment. But it's important to be aware that hurricanes, earthquakes, and floods can bring. Thankfully, they are not a threat to our part of the galaxy. There is still a chance that we could be hit by EVE. However, it's good to know that of all the issues we face, supernova-induced planetary annihilation is probably the one we can ignore. A roster. The zone of avoidance has finally been noticed by Vista. Some of the most amazing secrets in the universe are concealed, slightly outside the visible light's range. What if I told you that out of all the problems we face, supernova-induced planetary annihilation is probably the one we can ignore? They are seated just beyond our reach, enveloped in space dust. That's a bit annoying to consider. Isn't that about it? Up until now. This is a result of the European Southern Vista, the observatory's visible and infrared survey telescope for astronomy, allowing us to eventually lift the veil. We have a fairly complete infrared map for the first time in human history, one that breaks through the hazy mist of space to provide a previously unheard of perspective on our galaxy and its surroundings. See how this unique map was created, and enjoy some breathtaking photos that reveal previously unknown stars in our galaxy. VISTA released the largest and most comprehensive infrared data in September 2024. The survey of the Milky Way, spanning 13 years starting in 2010, produced 500 terabytes of data and about 200,000 photos. That is equivalent to the data required to stream a 4K video for almost 3 years in a row. VISTA is a component of the Paranal Observatory of ISO, which is situated in Chile. Its primary goal is to map vast swaths of the sky. The team was able to look through VISTA's Vera infrared camera. The gas and dust that fill our galaxy reveal some of the most obscure locations in the Milky Way. With conventional telescopes, we can observe space at visible wavelengths ranging from 380 to 700 nanometers. However, VISTA differs from conventional telescopes. VISTA uses infrared wavelengths between 900 and 1200 nanometers, rather than just visible light. This enables it to identify objects that would otherwise be invisible, such as dust-covered stars and cold brown dwarfs, also known as unsuccessful stars, that don't produce enough visible light to be observed through a conventional telescope. NGC 6357 is a nebula. One was captured in daylight, while the other using VISTA's telescope. In the infrared, we can observe that the dust that hides our field of vision appears to vanish, exposing what appear to be hundreds of millions or even thousands of stars that were previously undetectable. Survey. The Milky Way and its companion are known in Latin as Via Lactea project, also known as the VVVX or VVV Extended Survey. The information gathered from the VISTA Infrared Survey's 2 companion projects has already led to the release of over 300 academic publications. Unlike other recent space maps, this is one of the most intricate ever created. Nearly 80% of the Milky Way's luminous region is covered by this first infrared survey. Mass and offers the most comprehensive infrared catalogue of our galaxy's central area. It enables astronomers to examine our galaxy more thoroughly than ever before. This survey provides us with a precise 3-dimensional view of the interior areas of the Milky Way, which were previously obscured by dust. It includes a portion of the sky with roughly 10 times the number of full moons, 8,600, more items than any 2012 infrared map ever released. The Milky Way consists of a dense, bright, puffed-up central bulge and a group of stars with 2 spiral arms wrapped around the ends of a flat disk. The region of our galaxy that was mapped during the survey is depicted in this picture. The central areas are indicated by the red squares. Galaxies that were first observed by the initial survey and subsequently observed once more by the extended survey. Additionally, the areas that were only observed during the extended survey are indicated by other square colors. This image shows that the central plane of our galaxy has been the focus of these surveys, covering most of the nuclear bulge and part of the disk. However, what has VISTA exposed? Dante Maniti, an Argentine astrophysicist who oversaw the survey, stated, "We've made so many discoveries that our understanding of our galaxy has been permanently changed. It would probably be best if I just covered a few of the most significant ones in this video, even though I would love to talk about them all. We've made so many discoveries that our understanding of our galaxy has been permanently altered. Even though I would love to discuss them all in this video, it would probably be best if I only covered a few of the most important ones." VISTA focused on the star formation region of Messier 20 as part of the 2015 survey. The distance between Earth and the Trifid Nebula is roughly 9,000 light-years. When viewed in visible light, this image displays a magnificent nebula that is glowing. It is encircled by a pink haze of ionized hydrogen emissions and a blue haze of scattered light from young, hot stars. The cloud of gas and dust obscures the starry sky behind it. At this moment, take a look at the second image taken by VISTA's infrared camera. Beyond the clouds, there's a whole new star cloud. This image allows us to see our galaxy in a way that was unprecedented. To their surprise, astronomers determined that two faint red objects were variable stars. As they emerge, although they appear to be directly behind the Trifid Nebula's edge in the picture, they are extremely far away, roughly 7 times farther than the once helpful nebula, to keep them out of our sight. One type of bright star is seen as variable. It is erratic. Over the course of a few days or months, they brighten and fade based on how bright they are. Omicron was the first variable star discovered in modern times. Mira is another name for Seti. Up until 1638, it was referred to as a nova when Johannes Halwoods observed a cycle of brightness and dimness that lasted for 11 months. Regarding these two recently discovered stars, they are the only Ceph variables that we have identified so far in this location, which is located on the far side of our galaxy, beyond the central bulge. Additionally, they may be incredibly helpful as well. Consider them a type of cosmic yardstick that can be applied over tens of millions of light years. If you are aware of how you can determine the length of the star's pulsation period, from bright to dim. In addition to its age, absolute brightness can be compared to the amount of light that reaches Earth is known as apparent brightness. Thus, you have a gauge of how far away the star is. These kinds of reference points allow us to create a true illustration of the size of our galaxy and beyond. A group of astronomers and data scientists discovered even more potential seed stars by looking toward the galactic center. 35 of these 655 stars were classified as classical stars out of 2 classes. The one that is younger. This was particularly exciting because it was believed that the galactic bulge contained mostly elderly stars that are at least 8 billion years old. The team found that all 35 of these seafoods had pulsation periods of less than 100 million years old, with some of them possibly being as young as 25 million years. To put that into perspective, our Sun is roughly 4.5 billion years old. Thus, the youngest of them may be as young as 25 million years old. To put that in comparison, our Sun is roughly 4.5 billion years old. Thus, the youngest, just 0.6% of our Sun's life, has involved seafood. Another significant finding came from the team's investigation of seas. The team's mapping of the 35 classical Cephs they discovered allowed them to track a thin disk of young stars that is a brand new feature in the Milky Way, spanning the entire galactic bulge, concealed by dense clouds. It remained unidentified in every earlier survey conducted in the area. By revealing this structure in conjunction with the discovery of, as I previously stated, scientists have deduced that star formation has been ongoing in all the sea feeds for the previous 100 million years along the galaxy's midplane. Additionally, there may be even younger seafood that we haven't yet seen because these stars would be so bright that they would be covered in the VV pole. The discovery of this slender disk of young stars inside the galactic bulge is amazing. Previously, we believed that the galactic bulge was a long-gone characteristic of our galaxy's past where only old stars had developed independently of the stellar disk. However, this discovery shows that things aren't so clear-cut, and that the emergence of more recent stars in the bulge may be a normal development of the evolution of our galaxy. However, perhaps even more motivating is a discovery made at the ancient core of our Milky Way galaxy by the VISTA infrared survey. For the first time, an ancient star type called RL Ray was discovered in 2016. Ramos Rodrigo Andreas. Globular clusters are typically home to this kind of star, which typically revolve around the galaxy's outer regions. A globular cluster is a tightly packed cluster of stars with tens of thousands to millions of stars connected by gravity. Additionally, they are extremely old, containing a population of stars that may be older than 10 billion years. The group discovered 12 RL Ray stars during the VVV survey, indicating that they could be the remains of an old globular cluster located in the center of our galaxy. This discovery also provides evidence that could help astronomers decide between the two opposing theories regarding how nuclear bulges form. Although some researchers believe that the nuclear bulge develops early in the galaxy's evolution, when several smaller galaxies collide violently, others claim that it develops gradually over time. To start the formation of stars, gas is directed inward. Locating these old stars here indicates that the Milky Way's bulging center most likely developed as a result of primordial globular clusters merging. Consequently, the first theory is supported. Thus, it not only alludes to our own galaxy's origins, but it also provides strong evidence that these galactic bulges could develop in other comparable galaxies. As part of the 2011 infrared survey, VISTA discovered 2 new globular clusters. A globular cluster known as UKS-1 is visible in this visible light image of the globular cluster up until the latest findings. Now compare this same area of the sky, but this time in VISTA's infrared light. Suddenly we can see what we have been missing. Far fainter than the recognized UKS-1. We can identify a second globular cluster, designated VVV-CL01, which is located in the upper left corner of the image. Soon after, another globular cluster was discovered, appropriately named VVCL02, and this tiny, perhaps the closest known globular cluster to the center of the galaxy, is a faint cluster of stars, the universe. Did you know that only 158 globular clusters were known to exist in the Milky Way before VISTA discovered these new ones? Finding 2 more of these uncommon stellar objects through the survey is quite a notable achievement. In this galactic center, it's easy for younger stars and globular clusters to be obscured by cosmic dust because they are too old to shine as brightly. However, these characteristics present intriguing opportunities for additional research now that they have been identified. It might simply be a perspective illusion. However, researchers have questioned whether VVV-CL01 is gravitationally attached to UKS-1. In that scenario, they would be the first binary globular cluster pair in the Milky Way. We discovered binary clusters in other galaxies, such as the massive Melanic Cloud and Centaurus A. However, scientists believe that the most massive collision may occur when these gravitationally bound clusters collide, globular clusters such as Omega Centauri. Thus, researching a binary cluster directly in our own galaxy could provide some incredible insights into this process. It's all speculation at the moment, but it's definitely cool to think about. In addition to globular clusters, the VISTA infrared survey identified a multitude of other types of star groups. There are at least 96 new galactic or open clusters discovered, which usually have fewer, younger stars and are far more prevalent than globular clusters. They have been obscured by cosmic dust, just like the globular clusters, but VISTA's 4.114 infrared telescope has lifted the curtain to show them in all their glory. Take a look at the curtain has been lifted by a telescope to reveal them in all their splendor. Look at one of these open clusters, VVVCL03. VVVC03 is one of these open clusters. It is considerably harder to see in pictures than the densely packed globular clusters. Attempt to view the variations in star density between this area of the image and its surroundings. VISTA discovered it 15,000 light-years from the center of the Milky Way. The scope of this survey is astounding, covering a large area of the sky and charting over 1.5 billion objects. This information has already resulted in intriguing findings that are changing our perception of the Milky Way and beyond. And that's just the tip of the iceberg. Future telescopes and observations will build upon this survey, which should be able to build on the legacy of VISTA with even greater sensitivity and resolution. We now possess the most intricate 3-dimensional map of the Milky Way ever created. Structure and items, one that revealed secrets that were previously unattainable. Additionally, scientists are already discovering new galactic features and changing our perception of the galaxy. Using the data from this innovative infrared survey and the most recent visible light research from the ISS's Gaia mission, it's an exciting time to be an astronomer, and we can anticipate a wave of new discoveries about the universe and our own galaxy as a whole. Infrared observations from VISTA have revealed dozens of hidden stars, clusters, and millions of stars that had never been seen before. New stellar nurseries where stars are born have been discovered. They have expanded our knowledge of how our Milky Way formed. A new era of galactic exploration has been ushered in by viewing the sky through various wavelengths, and I can't wait to see what else Vista's 3D map will reveal to astronomers and data scientists. How far away is our closest neighbour, Alpha Centauri? Some of you may recall my very first video on my channel, which showed the size of our solar system in relation to the Sun. It was about the size of a soccer ball or a football. I'm going to repeat that today, but this time I'll scale it down slightly to the point where the Sun is as small as a grain of sand, only 1 millimeter in size. We will determine the size of the solar system. The size of the solar system is comparable to that of the Sun. So let's start with the Sun. I intend to, of course, Mercury is the planet closest to our Sun. Additionally, if the Sun had a diameter of Mercury would be 4 cm away. Therefore, I will place it simply by that location. Mercury is one of them. Venus is therefore the next planet closest to the Sun. The distance is 8 cm, so Venus is there. We on Earth are next, and that is 10 centimeters away. Tunes. Next is Mars, which is 16 centimeters away. The next one we'll discuss is Ceres' dwarf planet, which is located 30 centimeters away in the asteroid belt. Alright. Jupiter, which is 56 centimeters away, is next. Now we're getting far away. Saturn is 1 meter and 3 centimeters away. The first of the ice giants, Uranus, is located at a distance of 2 meters and 6 centimeters. The final actual planet in our solar system is Neptune, which is 3 meters and 24 centimeters away. So we'll examine our solar system. Please take a moment to follow me. Come on then. Come on. I know this wasn't really a straight line, but yes. Alpha Centauri, if the Sun was the size of just 1 millimeter, Alpha Centauri is 30 kilometers away. And that's our closest star. I appreciate you watching. All of the astronauts helped make this video possible, via Patreon. If you want to give them more stability and believe that these videos have some educational value, compared to the algorithm, you can contribute to their creation by becoming a paid Patreon member. When you sign up, you can ask our team questions, see your name in the credits, and watch the entire video advertisement for free. Simply use the link in the description to register. For more Astram in the meantime, click the link to this playlist. Richness. Next time, I'll see you.